Yeah, hello everyone. Are we expecting physical classes from next week? Aditya,
Yes, ma'am.
all of you will be in campus from next Tuesday, next Monday.
Ma'am, most of us are coming, but 100% we can't assure.
Okay. So if out of 120, if the strength is 100 plus, then we can definitely have physical classes.
Okay, ma'am.
Okay. We are left with three important topics. Sliding contact bearing, then rolling contact bearing, and wire rope design. So the sliding and rolling contact bearing, this is sufficiently large topic. Each numerical would be of different type. A lot of theory is also there in understanding the working of bearings. So for this theory part, I'll be using the PowerPoint slides. Okay, what do you understand by bearings? Or where do you need bearings? Arshini? In the rotating shafts. Okay, and how does these bearings help in the rotating shafts? Sarvesh? It reduces friction. Okay, good. What else? What else? Separates the fixed component from the rotating component, helps in carrying load. Yes. These bearings are also withstanding the load which the shaft is carrying on it. So it helps in reducing the friction. It allows the smooth rotation of the shaft inside the bearing. It has to carry load, it has to resist axial load, or it has to carry axial loads also. What is your point, Dave?
They restrict actual movement of parts.
Movement will restrict, yes. They will sustain these axial forces along with the radial forces, but they'll not let the shaft vibrate in the axial direction, right? This is your point, right?
Yes, ma'am.
Okay. So what should be the length of the bearing? What should be the diameter of the bearing? What should be the diameter of the shaft? What should be the thickness of the oil? And how effectively the heat should be dissipated, because you understand whenever there are two moving parts or one part is moving, another is stationary, and there's a relative motion, heat would be generated and this heat needs to be dissipated. So we have to also think from heat dissipation point of view. We have to take care of coefficient of friction. Then what is the load it is carrying? What is the load that shaft is carrying? How much, what is the share of that load on each bearing? So if you remember in your second year solid mechanics, I guess you have solved so many problems on beams wherein you are calculating what is the load coming on each bearing. And now from that load calculation, we have to find out how this bearing is designed. So there are a number of variables or parameters which we need to consider now for bearing design. So there are two types of bearing. One is the journal bearing and another is the anti-friction bearing or the rolling bearing. We are starting with the journal bearing or the sliding contact bearing. What do you mean by journal? Looking at this image, can you tell me what is the journal from the bearing perspective? Ayush, Rajwal,
Shaft.
yeah, it is the shaft or it is the projected part of the shaft which goes inside the bearing. So this is shaft, and after the shaft there is a step down of the shaft, or there is another projected part with little smaller diameter as compared to the shaft. And that goes inside this bearing, where this part of the bearing, the outer covering of the bearing, this is stationary, and then there is this journal which is a part of the shaft but not the shaft itself, since the diameter of the journal and diameter of the shaft is different. But for all practical purpose, for all the calculations that we'll be doing, we'll be assuming the diameter of journal same as diameter of shaft. But ideally, for the assembly or for the actual bearing installation, you will see that the diameter of journal is little smaller than diameter of shaft. So you have to understand what we do in theory or in calculation and what exactly is done in the real life situation. So, and there is a layer of oil or a lubricant between this rotating journal and the fixed bearing. So, as the definition goes, a journal bearing is a machine element which is supporting another rotating element, and this rotating element is a shaft or it's an extension of the shaft, what we call as journal. So this has to support the shaft, it has to ensure that the shaft is rotating without friction, it has to carry the load and permit relative motion between the contact surface. So if the diameter of the journal is too large or the diameter of the bearing is too small, and if it is kind of locking, and if it is not permitting the shaft to move, then the design of bearing is failed. Which means it has to carry the load and it has to permit the relative motion between the two surfaces. Then, as you rightly said, why a bearing is required? It is required to reduce the friction between the two moving parts. It has to take care of the wear. The wear should be minimum possible because one part is continuously rotating. It would be rotating at a speed like 1440 RPM or 1200 RPM. And it is continuously in operation maybe for 22 hours a day or for 18 hours a day, working for say 5 years, 10 years. It will undergo wear and we have to ensure that this is minimum possible. And it should also help in dissipating the heat which is generated. So the job of heat dissipation, reducing the wear, reducing the friction, this is done by the lubricant which is provided. What kind of lubricant is provided? Do you have any idea? What kind of lubricant is provided? Karthik? Grease? Are you sure it is grease? Yes, it is mineral oil, Pradhiman, you are right. It's mineral oil. Normally, SAE grades of mineral oils are used, which are most commonly used. And there can be grease in some applications, but for limited application, but for most of the bearing, SAE grade of mineral oils, they are used. We'll see depending upon temperature how to select the oil. The purpose of this oil or the lubricant is to separate the bearing from the journal. The journal and the bearing, they should not come in direct contact with each other. There should always be a minimum thickness of the oil. This is very important. And since it has to dissipate heat, this oil is continuously leaking or it is flowing away, and it has to be replaced with fresh oil supply, which ensures that the heat is dissipated. Suppose you put grease for one time, how would this heat get dissipated? So the flow of oil or leakage of oil is also ensuring that heat is dissipated. Is that clear? Why oil instead of grease? Okay, good. We'll come to graphite as the material used. Now talking about the type of contact bearing based on the load that it is carrying. So now this is the journal or the projected part of the shaft, and this is the bearing. This is the length of the bearing, L. Capital D is normally designated as the diameter of the bearing and small d is the diameter of the journal. And since these two diameters are different, because of the weight of the shaft, the centers will always be eccentric. They will not be concentric. So the distance between the centers of the journal and the bearing, this is known as eccentricity. This is a kind of bearing which will withstand only the radial loads, the load coming along the radius of the shaft. And so this is the design. But if there is an axial load, in which kind of machine elements there would be axial load? Which kind of gears? Gears, specifically, can you tell me? Helical gears, yes. So if there is per gears, we know that it's only radial load. But in case of helical gears, in case of worm gears, worm and worm wheel, you will also get the axial component of the load. And if there's an axial component of the load, then this journal will start moving axially inside the bearing. And to lock this, we have to provide a collar. And the moment a collar is provided, this becomes an axial load bearing. So the bearing which can withstand the axial load also. The axial load is coming along the axis of the shaft. So this is in the direction P, and it is resisted with this P here, a collar inside the cavity. So there can be a single collar, there can be multiple number of collars depending upon what is the load, magnitude of the load, and depending upon what is the size required. For a very small sized bearing, small diameter bearing, a single collar might not be enough. So you will have to give 3, 4, 5 collars of small projected height. For a large bearing, even a single collar with this much thickness and this much height might be good enough. And then there is for a combined loading, like in case of helical gear, which is subjected to both radial as well as axial, you have collar at one end. This is sustaining the axial load and this is sustaining the radial load. So this is a combined load bearing. We have to design based on what type of load it is subjected to. So as I told you, after we finish off with this bearing and wire rope, next month when you will be physically here, we'll be solving assembly problems. And the moment you are designing a shaft which is carrying the helical gear, and you know that it is helical gear, you have to design the bearing which can take care of axial as well as radial loads. So simply designing bearing makes no sense because you don't know what are the loads on the shaft. You don't know what is the load on the bearing. And likewise, you cannot simply design a shaft without knowing what type of bearings you are using. So as you remember, we have designed the shaft only based on which parameter? Saurabh? Saurabh?
Yes, ma'am.
We were designing shaft based on which kind of load till now, and whatever problems we have designed the shaft. Amer? Bending? Did we design it for bending? How did you calculate the shaft diameter based on bending? Divakar, Prajwal? Radial load. Did you design the shaft for bending moment or for the torque or for both? Only for torque. Why not for bending moment? Beneath. Why only for torsion? Why not for bending? For length, we go for bending. So because the length of the shaft was not known, or because the distance between the two bearings were not known, so we assume that there is no bending moment. And how did we compensate for zero bending moment? Harshil, how did we compensate for zero bending moment? By reducing the maximum shear stress to 40 MPa from 75 MPa. So we know that shaft is subjected to bending, but you can find out the bending moment or the bending stress only when the length of the shaft is known, and the length of the shaft is the length between the bearings. So now when we will be solving the assembly problem, the location of bearing, the right hand side bearing and the left hand side bearing on the shaft and the distance between two bearings, that would be known. Then we'll be designing the shaft based on bending. Well, next classification is based on thickness of the oil or the lubricant. So you can see that the first one is a hydrodynamic lubrication, wherein you can see a uniform thickness of oil between the journal and the bearing. And the third one is the extreme case where the journal is in contact with the bearing. Whereas there is a mixed lubrication case wherein only a small part of the roughness of the surface of the bearing and the journal, they are in contact with each other. But in case of hydrodynamic lubrication, which is also known as thick film lubrication, the working surfaces are completely separated. This is the most commonly used type of bearing. And while we are solving the numericals, we will always assume hydrodynamic lubrication. So I repeat, hydrodynamic lubrication is when a thick film is formed, and the thick film is thick enough to keep the journal away from the bearing. There is no contact. While solving the problem, we'll talk about the surface roughness of the bearing and the surface roughness of the journal. Howsoever neat the polishing is done, there would still be some roughness in microns, and even that roughness will lead to contact between the journal and the bearing, and that will make it a mixed lubrication, and this will increase the wear and tear. And the boundary lubricated bearing or the boundary lubrication is known as the thin film bearing or thin film lubrication, wherein the lubricant is present, the surfaces are still partially in contact. So somewhere they'll be in contact with each other. So this is used whenever the magnitude of load is very, very small. But for heavy loads, we have to go with hydrodynamic lubricated bearing. So even if there is hydrodynamic lubrication, mixed lubrication, boundary lubrication, we will be assuming by default that we are designing for a hydrodynamic lubrication. What should be the property of this bearing material? Now this is the outer gray hollow donut shaped thing. This is the bearing. What do you think should be the property of this material? We have to select a material, and for selecting the material we should know what properties we are looking for. Wear resistance, yes. Hardness, good. What else? What else? Heat dissipation capacity. A material is having good heat dissipation capacity. What does that mean? What property it should have? Good thermal conductivity, yes. Tensile strength. Do you think it is subjected to tension? Bearing is subjected to tension somewhere? When a journal is continuously rotating? Toughness, again, if there is an impact load. Endurance is yes. I still am stuck up with the same point. Tensile strength. Do you think this is subjected to tension, Daitwa? Daitwa?
I'm during, due to the radial forces, maybe.
Due to radial forces also, it is subjected to compressive load. The load is coming from the inner surface outwards, right? So it is rather
Yes.
subjected to compressive stresses. So it should have good compressive strength. From manufacturability point of view, can you say something? I gave you a material which is very tough, very hard, but you should be in a position to fabricate it or manufacture it in a perfectly round or perfectly circular shape. So the most important property is the compressive strength because it is continuously subjected to the load due to rotation of the journal. And this journal is trying to exert force from the inner periphery of the bearing, and so it should have a good compressive strength. Somebody talked about endurance. So this has to withstand maybe millions of cycles before it fails. And so it should have good endurance or fatigue strength. From manufacturing point of view, conformability. What is thickness? Rakesh, what do you want to say thickness as a property? Rakesh? Are you there? So conformability is it should conform to that shape which is required. So essentially it should be in a position to get the perfect circular shape. Nobody talked about the corrosion resistance. Since it is made out of metal, it would corrode with continuous use. And if the surface of the bearing corrodes, then the friction would again increase. And our basic aim is to reduce friction. And hence it must be corrosion resistance. There are special materials like babbitt or carbon graphite, which are very costly, and many a times entire bearing is not made out of this material, but only the inner layer of the bearing is coated with the special kind of material which will possess all these properties. So if you are using a special material, it should possess the ability to bond with the parent material or the other material of the bearing. That is bondability. So it should have a property to bond with the parent material. And from heat dissipation point of view, it should possess thermal conductivity. So it should help in dissipation of heat. So among various properties, these are some of the most important properties. So Rakesh, you are there, 88? Rakesh? Okay, leave it. So these are some of the important properties. Yeah, Rakesh, what was your point? You said thickness as a property. Thickness of the bearing, is that a property? Its length or its thickness or its diameter is what we are designing, right? Now, if we know these are the properties, then we can select the material. What is Babbitt? Anybody knows what is a Babbitt material? Anyone can tell me? It's an alloy, and it's an alloy of either tin or it is alloy of lead. So if it's a tin-based Babbitt, it will have 90% tin and the remaining would be copper, antimony and lead. And if it's a lead-based Babbitt, it will have 84% lead and rest would be tin, antimony and copper. So these are the Babbitt materials and these are specifically used for bearing because it possesses the properties that we have discussed. So the most commonly used material will be the Babbitt material, and we'll get the properties of these material in our design data book. Then gunmetal is used, again another alloy, which is used normally for high speed and for high pressure. So those bearings which are designed for high speed of shaft and for sufficiently heavy loads. Then phosphor bronze, which we were using for worm and worm wheel. This being a costly material, this is used for very high pressure and for very high speeds. So while solving the numericals, we'll see what is high speed and what is very high speed. Accordingly, we select the material from the data book. Alloy of silver is also used for aircraft engines where again there are so many rotating parts and the bearing needs to be having all those required properties and at extreme conditions, at very high pressure, maybe at very low temperature, at different humidity, rotating at very high speeds. So these are used for aircraft engines. And then as I said, carbon graphite, this is a special kind of material which has self-lubricating property. Anybody can comment on what is self-lubricating? Anyone can tell me? Devansh? Manan, you are there? No need for external lubrication. Yeah. So how do you think it? Yeah, it is impregnated with lubricant at the time of manufacturing, and every time it rotates, it can lubricate itself, and there is no need of external lubrication. And so this is known as, yes, it is known as self-lubricating. So these are some of the materials used, and then there are many more, but these are the most commonly used materials for bearing. Now let's talk about viscosity. You have studied about viscosity in your fluid mechanics. Now from bearing perspective, say this is a plate which is moving at a velocity u, and this is the stationary plate. In between there is a thickness of oil. Now the layer of the oil which is close to the stationary part, this will have velocity 0, and the layer of the oil which is near this moving part will have its velocity u, whatever is the velocity of the moving plate. Intermediate layers will have different velocity, and this velocity small u would be proportional to the distance from its stationary part or from its moving part. So this du by dy, this keeps on changing, and this is the maximum film thickness h, and this is the force with which the plate is moving. So this is the analogy for the journal bearing, which is rotating inside the bearing. The journal or the shaft rotating inside the bearing, having a thin oil film which is continuously getting sheared off, because one end of this oil is having zero velocity, other end is having the required finite velocity u. So what happens here is, when there is a film of lubricant or an oil of thickness h, and this is trapped between a moving plate and a stationary plate, this oil film is continuously getting sheared, and the velocity of each layer is different, and it depends upon what is its height or what is its distance from either the stationary plate or the moving plate. So normally we'll consider from zero, that is from the stationary plate. And the fluid friction is because of the viscosity of the oil and due to the shear rate of the fluid, the rate at which the oil film is getting sheared. And the formula given is the shear stress tau is equal to Z, where Z is the viscosity, into du by dy, where this u is small u. So this is continuously varying with respect to y. So this is the shear stress, and Z is the viscosity of the oil. Please take down these points. Now when the oil is continuously moving and there is a friction between the rotating part, there is a frictional drag, and this frictional drag is coming into picture because of the viscosity of the oil, because the journal is rotating at certain speed, and there is a heavy load on the shaft which is taken care by the area of the bearing. So area of the bearing is length of the bearing multiplied by its diameter. Okay, before we go ahead, what is absolute viscosity and what is kinematic viscosity? Vandana? What is this Z? Is that kinematic viscosity or that is absolute viscosity? Z is absolute viscosity, also known as dynamic viscosity. Yes. And by definition, it is the measure of the internal resistance or the tangential force per unit area to move the plate with respect to another plate. What is the unit of absolute viscosity? Unit of absolute viscosity, poise. And what is the unit of kinematic viscosity? Stokes. Yes, you're right. So we are here discussing about the absolute viscosity or the dynamic viscosity. And the frictional drag which is coming into picture, this is proportional to this absolute viscosity Z. This is proportional to the journal speed N and a load carrying area. So this area will be given by L into D. And the coefficient of friction between the two materials due to oil, this will be again proportional to viscosity. This will vary with speed, and this is inversely proportional to pressure. Now these equations, they are quite complicated, and in the design data book we have lot of graphs for different parameters. And as I said, there are a number of variables while we are designing the bearing. So out of say 6 or 7 variables, 4 would be known, 2 would be missing, and we'll be referring to all those graphs that are given in the design data book. Do you have your Shivalka design data book with you? I'm sure you have the soft copy. Please open page number 134, BD Shivalka design data book. BD Shivalka design data book. We are going to have a quick look on the graphs that are given. What is figure 13.2 indicating? Page number 134, figure 13.2. Kaustubh?
Ma'am, temperature viscosity relationship.
Correct. So with temperature increase in the temperature, how the absolute viscosity reduces. And there are different grades of mineral oil, turbine oil, or SAE grades of oil. So we will be selecting based on temperature and viscosity which oil we want to use. What is the next graph? Figure 13.3. Next graph, same page. Vedant, you are there. Sommerfeld number versus coefficient of friction. So we are coming to what is Sommerfeld number. So for solving these numericals, we'll be referring to all these graphs. If you can quickly turn pages. So for different L by D ratio of the bearing, we have so many parameters, so many variables that we'll be referring to. So these formulas, as I said, they're quite complicated and we are not going to use formulas. We are going to use these graphs which are plotted for coefficient of friction versus Zn by P, where Z is viscosity, N is the speed of the journal, and P is the pressure, average pressure. Similarly, the frictional drag versus Zn-A. So let's see the mechanism of journal bearing, how it rotates. Then we go for the variables and then we see what are the relationships. So this is at the rest. When the shaft is not rotating, this is the bearing and this is the shaft. And the shaft is carrying some static load, weight of the shaft itself, plus the dead weight of the gears or the pulleys or the sprocket, whatever the shaft is holding or it is carrying. So at rest, this is completely settled down at its base. The moment it starts rotating, we are assuming this is rotating in anti-clockwise direction. This journal has a tendency to lift towards or away from the direction of rotation. So if it is rotating in anti-clockwise direction, the journal gets lifted towards left. And the moment a uniform film is formed or the hydrodynamic lubrication is formed, this entire journal will shift and move towards right if it is rotating in anti-clockwise direction. If the rotation is clockwise direction, these two images will be swapped. So it starts like this, and when it keeps running, it lifts here. And we have a journal bearing test set up in our lab. And normally we do have experiments on this machine wherein you can actually see a shaft rotating inside the bearing. Everything is exposed. We measure the pressure on the periphery of the bearing and we get a plot how this is the initial position, how it lifts on this side at the starting, and then it reaches this position with a pressure distribution film formed over here. Unfortunately, because for last 2 years there were no classes, no practicals held, this machine is out of order now, and I'm trying to get it repaired so that I can show at least some experiments to you. So wish me good luck for this. So this is the journal and this is the bearing and this is the pressure from the oil. And from the side view, if you see that the oil pressure is distributed like this while it is running at its normal speed. So the pressure is minimum at this point, it increases to maximum and it again reaches its minimum. So there is a wedge of the film which is formed with minimum film thickness somewhere here, and the thickness of the film increases on the either side. So it is the oil or the fluid which is getting squeezed between the two surfaces having relative motion. So this is how the oil film is formed and the pressure is getting distributed. So we are coming to the expression of how the pressure changes with the thickness of the oil and how the shear stresses changes with the thickness of the wedge. So you have to understand that it starts in the rest position, initially it has a tendency to lift towards left while rotating in anti-clockwise direction. And when it reaches its normal speed or full speed, the entire journal will be lifted up towards the right side, and this oil is exerting pressure on the journal and it keeps it lifted here. And since there is no contact, this is running absolutely smoothly without any friction, without any wear. So this part is clear? If yes, then we proceed with the next slide. Ambika, is that clear? Ambika? Okay.
Yes, ma'am.
Okay. So a few more parameters before we start finding the relationship between them. To get this right figure first, this is the journal, the projected part of the shaft, and this is the bearing. And there is a thickness of the oil, which is shown in pink color. This is the length of the bearing L, and this is the diameter of the journal. So this L by D ratio, this is very important. You must have seen in the graphs that we were referring to, each curve is indicating different L by D ratio. L by D ratio may or may not be given in the problem, and we have to assume an L by D ratio of 1.21, 1.5, something like that. So what is the significance of L by D ratio? Well, we are coming to it. So along the length, this is how the pressure is distributed. Minimum pressure at the ends, maximum pressure at the middle point of the length. And in the side view, if we see that this is the journal, this is the bearing. The moment it starts running at its full speed, these two centers, the center of the bearing and the center of the journal, they are rotating eccentrically. And this eccentricity E is maintained. So we'll also be getting the value of E in the numerical, or you have to calculate what is the eccentricity from those graphs. So this is an important term, E. And then there is an H minimum, which means minimum oil film thickness. So this is another very important parameter. We want this minimum film thickness to be as large as possible or as small as possible. What do you think? It should be as large as possible to maintain that this is or to ensure that this is hydrodynamic lubrication. So we want this H minimum to be maximum, H minimum to be as large as possible, and accordingly we'll see how the graphs are plotted for H minimum versus other parameters. Then you can see there is a pressure P which is acting on the journal, which is getting transferred to the oil, and then the oil is getting sheared. Capital D would be the diameter for bearing, and small d would be the diameter for the journal. So other parameters for now you can ignore, but I want you to draw these figures, mark eccentricity, mark H minimum, label L, label D, and label or mark this pressure distribution curve shown here. Because these variables we'll be referring to many times. Please draw a rough sketch. So the important parameters are L, D, pressure P, load coming on this, F, we'll mark it F because small p we are using for pressure, H minimum, and eccentricity E. Assuming you are done. Will not define these terminologies. So there are a few terms, few parameters which are important from solving the numerical. Diametral clearance. So diametral clearance is normally given by C, which is the difference between D and D. So what is capital D and what is small d? Pressure is, we are coming to it. We have not discussed about why this is the kind of pressure distribution. So we are coming to it, Prajwal. Let me discuss other variables and then we can discuss about this. So what is capital D and what is small d? Capital D stands for capital D is the diameter of the bearing and small d is the diameter of the journal. So this is the term diametral clearance. Now you have to be very clear that this diametral clearance C, eccentricity E, and minimum oil film thickness H minimum, these are three different variables. So diametral clearance is a difference between the diameters, eccentricity is a distance between their centers, and H minimum is whatever is the film thickness formed at the minimum height, whatever is the minimum film thickness formed because of the pressure distribution. So why this H minimum has to be maximum? What is the magnitude of H minimum? And how the pressure distribution varies, this part we'll be discussing in the next class. For as of now, I want you to go through these terminologies. So few books will be giving the value in terms of diametral clearance, and other books you will find the radial clearance, which will be half of diametral clearance. So we'll be using the term say C1. And then there is a ratio of the clearance and the diameter, which is the diametral clearance ratio, which is C by D. So where C is the diametral clearance and D is the diameter of the journal. So some of the graphs are plotted for coefficient of friction versus diametral clearance ratio, where it is C by D, where C is the difference between the two diameters. Then eccentricity, as we have discussed just now, eccentricity is a distance between the center of the bearing and the center of the journal at full load. So as the load goes on increasing, this eccentricity value might change. Read it A and D and. Whereas this clearance, this is fixed. This is not changing with speed or this is not changing with the load. But H minimum and eccentricity, this would change. H minimum would change. So H minimum, also known as minimum oil film thickness, this is a parameter which depends upon the type of oil, the viscosity of the oil, it depends upon the RPM of the journal, it depends upon what load it is sharing, what type of load it is withstanding. And so this is one of the important parameters in the journal bearing design. So it is a minimum distance between the bearing and the journal when it is fully lubricated. So fully lubricated is hydrodynamically lubricated, which means there is a layer of oil continuously separating the two moving surfaces. So at no point the two surfaces of the journal and bearing will come in direct contact. That is the meaning of fully lubricated condition, or that is the meaning of hydrodynamic lubrication. So there are, I'm repeating, there are so many terms and all those terms, they are interdependent. So unless we understand this, we cannot proceed with more terms. Okay, I was talking about the length of the bearing and the diameter of the bearing. So depending upon what is the ratio of L and D, we define what are short bearings and what are long bearings. So if L by D is 1, which means it is a rectangular bearing, so this square bearing. This will also be called as a square bearing or a small bearing, which means the length is equal to diameter of the journal. If L by D is less than 1, then we call it short bearing. So length is less, diameter is large. We'll see what are the advantages and limitations of each one of them. And if L by D is greater than 1, so the value might vary from 1.1 to 1.8 to, that would be termed as long bearing. So if you refer the design data book, the minimum value for L by D is given as 1/4, so 0.25, which would be a small bearing. Then you have graphs for L by D 1, which is the short bearing, and for L by D value, maximum of 2, and then on the higher side it is given as infinity. So anything above 2 is infinity. Now you cannot have an infinite length bearing. But then you get graphs for L by D 1, L by D 2 and L by D infinity. So normally we will be in a range of L by D 1 and 2 normally, unless it is mentioned in the problem that the value is 2.2 or 2.5. Now, depending upon what is the pressure distribution, we get an average pressure. And when this average pressure is multiplied with L and D, this decides what is the load carrying capacity of a journal. So load carrying capacity is average pressure multiplied by the cross section area. And so L by D ratio, this is very important because this decides what is the load carrying capacity. So when the L by D is large, the load carrying capacity is more because the value of L is more, W increases. So it's preferred to have a long bearing over a short bearing. But then what are the disadvantages or advantages of long bearing? If it's a small bearing where L by D ratio is less, equal to 1 or less than 1, this pressure which is varying between the ends, if this L is small, this is very acute, this is very sudden. So it starts from minimum, it reaches maximum and it drops here again. So this pressure drop is sudden. Whereas for long bearing, you get a more smoother curve for pressure distribution. For small bearing, the oil will be continuously leaking because this length is very small to hold the oil and the oil is continuously leaking. And because there is a leakage of oil, you have to continuously supply oil. So more amount of oil is required, although this oil is circulated, but then you have to continuously supply oil if it is a small bearing. So from this perspective, larger L by D is good, but with larger L by D, oil leakage is less, and if oil leakage is less, then heat is not dissipated. Continuously, if the oil is leaking and you are supplying fresh oil, this is also taking into account the heat dissipation. So heat dissipation is better when L by D is small, but then it calls for lot of oil leakage. Pressure distribution, so depending upon what is your governing parameter, if the amount of heat generated is large and you want the heat to be effectively dissipated, you should go with small L by D. If you want the pressure drop to be more gradual, then you should go with larger L by D ratio. If you don't want the oil to be supplied continuously, you have to go with large L by D, but then it will not remove the heat effectively. So as I said, there are so many parameters, and when you are selecting L by D, you have to keep so many things in mind. A numerical may not give you all the details, but with some hint, continuous oil will be supplied. So if that is given, it means you can go with small L by D ratio. Or excess amount of heat would be generated. If this is the point given or mentioned in the numerical, it means that you have to make sure that heat is effectively dissipated. Or the problem statement says that the pressure drop should not be sudden. You must select larger L by D ratio. So next class we'll discuss more about variables, and then we'll talk about the pressure distribution based on the shear stress, based on the thickness of the oil and the viscosity of the oil. I'll be going a bit slow here because there are so many variables before we actually start solving the numericals. So again, next class will be more of theory and then we'll start with numericals. Okay, do you have any questions till now? Else we'll stop here. Anybody has any questions to ask? Okay, no questions. So we'll stop here for the day. Thank you all of you.